Well, welcome everybody to the third in our series of webinars. I know everybody's working from home, or at least a lot of people are, and you're out of the field. And we thought it would be a good time to provide some knowledge transfer to all of our friends out there. So hope everybody is staying safe. Again, I'm a bit of a newbie at this, so just bear with me on this. We're really trying to make these educational. These are not sales pitches. I get very enthusiastic when I talk about the subject of maturity, and maturity does come up with mass concrete. So I want to make sure that I put that out there that if you hear that I'm all enthusiastic, that's the reason. So quick background: I've been doing this about 20 years. I'm on a couple of committees at ACI, American Concrete Institute, and ASTM, including the committee that writes the standard for maturity. I hope that my experience in this emerging field is helpful to all of you watching today. I do want to add a little bit of a caveat regarding mass concrete, the subject of mass concrete. This is a highly complex subject with lots of moving parts. And the ACI documents covering this subject are long, detailed, and I didn't know this, but they span 3 or 4 entirely separate sections of guidance. Now, I always knew that mass concrete was covered under ACI 207, but I had no idea that there were subsections of 207 that cover in great detail certain aspects of this subject. So I have learned a lot in the past week getting ready for just this seminar or this webinar, and it really should be called Mass Concrete Light, because this is going to be a general overview of the subject of mass concreting, and it's going to touch on areas where I do have extensive experience, but this is no substitute for expert engineering advice and direction that you should enlist for any truly massive concrete placement. Should be about a 30-minute webinar. If you have any questions, there is a button down below or to the side on the website where you can ask questions, and hopefully we can answer those live. But any question that does come to me will be answered directly. It comes directly to my email, so I will definitely answer those. So without further ado, what I really want to do is talk a little bit about mass concreting today, and the applications for temperature monitoring, and also the applicability of maturity when doing mass concreting. Hopefully this webinar is going to provide some tools for better decision making during construction. What we're going to cover today is the definition of mass concrete, and along with a bunch of considerations that any contractor should think about when they are placing massive concrete elements, such as structural design criteria, mixed designs, supplementary cementitious materials, and things like that. And we'll go over all of this. Placement temperatures and in-place temperatures and strengths, and all sorts of other stuff, and hopefully using all of this information in our planning and using this knowledge, which is very important. And I will say definitely be aware of the ACI 207 documentation. So within ACI 207, which is the mass concrete spec, there is a very short, succinct definition, which is mass concrete is defined as any volume of concrete with dimensions large enough to require that measures be taken to cope with the generation of heat from hydration of the cement and the attendant volume change to minimize cracking. So it really is all about trying to make sure that the concrete that you place, this massive concrete, doesn't crack. That's the goal. I would highly recommend, if anybody is interested in it, to pick up ACI 207.1R, which is the latest version of the mass concrete spec. And it's the intro spec. There are several others, but there's a great section on the history of mass concreting. It was fascinating to read, had no idea, and it's really pretty interesting stuff. So not going to get into it here, but definitely read it if you're into history. So as far as mass concrete for structural design and the engineering of mass concrete, mass concrete is used when you need certain durability and obviously you need structural integrity for a bridge, a dam, anything like that. There are definite structural design criterias that have to be met. For example, durability. This mass concrete can't just fall apart in 20 years. You don't want it to be durable. You want to make sure that when you're building, that you do this with economy in mind. Certain aspects of and mixed designs, for example, or even the economy of placement, the economy of the construction process itself has to be considered. You have to consider the thermal action of the mixed design that you are creating, because you can have a mixed design that sounds great in theory, but that might not function well in practice. And ironically, mass concrete, you would think that strength would be a big deal, and it's not. It's almost always a very much a secondary concern. Part of the reason for that is that the strength of the mass concrete is rarely an issue, because it's mostly the mass that is doing the structural function, not necessarily the strength. So there is so much in ACI 207 that talks about mixed design considerations that it would just be a disservice to 207 to talk about it here in a quick little webinar. But they do point out that thermal action and adiabatic behaviors is a very important consideration when you are creating a mixed design. And what that means, if you do not know what adiabatic, or some people have referred to it as semi-adiabatic, uh, these are behaviors where when you create a mix design, that mix is going to behave in a certain way where when you mix the concrete at one temperature, that no matter what, that mass, that concrete mix is going to rise a fixed amount. It's the adiabatic rise. That is a property of a mixed design. So if you have a mixed design that has, let's say, 300 pounds of Portland cement, and you place it in a mass, you know how many degrees that mass is going to rise at its core. That is the adiabatic behavior that you're looking for. We'll talk a little bit about how you can look at that, how you can evaluate it in a little bit later on. And then there's workability. You have to be able to have a mixed design that's also workable. It has to be pumpable, or maybe not. Maybe you're going to use buckets. How is the concrete going to be placed? There are a lot of other variables. I mean, a lot of other variables that are addressed in 207, such as the control of the water cement ratio, the placement temperature, the size of the aggregate, the cleanliness of the aggregate, for if you can believe that. Everything goes into anything that goes into quality concrete is magnified when it comes to mass concrete. Sometimes the availability of certain good supplementary cementitious materials that could be a benefit in mixed designs, that they might not be available. So for example, in certain parts of the country, slag isn't available. It's just not an option. Slag happens to be a very good supplementary cementitious material for mass concreting. So in those people in those areas have to do something else. They have to use another type of supplementary cementitious material that is going to keep the heat of hydration down. A lot of these considerations are all geared towards keeping the heat of hydration low um, uh, from the beginning. And then, as I said earlier, strength is almost always a secondary concern. Pretty much any mixed design is going to get to the certain strength that is needed for that project. So what are some of the other considerations are, obviously you need a low heat of hydration cement, for example, like a type 2. It's pretty rare that people are using a standard type 1 cement these days, unless you have a very high percentage of slag. And I'll talk about that in a minute. They One of the things that they stress in the 207 document is that mass concrete mix designs typically have very low cement factors to begin with. Some of them are ridiculously low. There was one that they cited in the document where it was 185 pounds of Portland cement, or actually total cementitious materials per cubic yard, which that's unheard of even as recently as 20 years ago. So there have been a lot of advances made in even the past 10 years of understanding the effects of these cementitious materials. They do talk about in the document that air entrainment can really aid in workability, even in situations where freezing and thawing isn't a big concern. So if you are working with mass concrete and you have no other way to improve the workability of your mix, you can consider adding an air entrainment admixture, even if you're not going to be subjecting the concrete to freezing and thawing. There are plenty of admixtures that they cite to reduce the water requirements while also improving workability, and also something called pot life, which is uh, the ability of the concrete to stay fluid inside the mixer, and also delaying set times so that all of the concrete sets up together. So there are a lot of ways that you can play with the chemistry and the recipe for your concrete mix design to get just what you need. And SCMs, supplementary cementitious materials and other pozzolans, are really important when it comes to a mass concrete mix design. Um, they, they are they tend to be products that react with Portland cement hydration to become like a cementitious material. In other words, it actually takes the Portland cement hydration to kick off the reaction of something like a Class F fly ash or blast furnace slag. And that is something that a lot of people, when they're first starting out with a mass project, might not understand that your concrete, this mass concrete design, is designed intentionally to kick off very slowly, and they can be frustrated by that because they think their concrete isn't gaining strength. Very often, their early age test cylinders, for example, if they were to take a 7-day break, they might be extremely low because of the intentionally delayed hydration reaction. So it's just something to be aware of. One of the big aspects, and to be honest with you, it's a big aspect of not only mass concreting, but of course it's a big aspect for Con-Cure, because that's what we do. We make temperature monitoring equipment, but temperature control of any mass concrete mass element is very important. There are multiple ways. They cite 4 different ways to control the temperature of your mass element. The first is with what they call pre-cooling. And pre-cooling simply means you're going to cool the aggregates. You're going to use potentially ice for your mixed water. You might use liquid nitrogen to cool the mixed concrete, and you're going to ensure low placement temperatures. So what that basically means is, instead of, in the dead of summer, placing your standard 90-degree concrete, you're going to intentionally make that concrete something like maybe 50 degrees or 60 degrees, just because you want that low temperature to start off with, because you've got that adiabatic rise to contend with. And then the other thing that you can do, and it's not, I don't know how often it's done these days. I've actually never been on a project where they had to run pipes through the structure, but post cooling is where you'll run pipes through a structure and run either cold water or something else that removes the heat from the inside of the mass. It's kind of, that's one way of doing it. Apparently, with very massive structures, that's still common. I've not worked on one that ever needed that. So, and then we touched on this a few minutes ago, but using the mix designs to keep that heat of hydration low, and again, knowing that adiabatic temperature rise via extensive pretesting is important, because the placement temperature plus the maximum temperature rise, that adiabatic temperature rise, is the peak temperature that you can expect inside the mass. So that this little equation here determines your maximum allowable placement temperature. If you can't exceed, I'll just throw a number out there, 155 degrees, and your maximum temperature rise for that mix design is 65 degrees, then your maximum placement temperature is 90 degrees. Typically, you're going to want to place concrete at much lower temperatures than that. And as long as you know that the maximum peak temperature value will not be exceeded during the initial weeks as it's curing, then all you really need to do is to keep the differentials from getting too high, because that's another factor for mass concrete is the maximum differentials, which is the difference between the core, the center of that mass, and the outside edge of that mass. And the way you do that is by using insulation. And here's an example of some of these extensive pre-testing that gets done very often. Here's an example of an insulated cure box or an insulated box. It's about a 1 meter by 1 meter cube, or I just said one cubic meter. And what we do is we'll place sensors in a variety of locations inside this mass and monitor them. If you see right here where my mouse is, there's one of our recording devices, and we've got all these sensors that are ready to go down inside this concrete. And in fact, here's a picture of us putting one of the sensors down along the corner or the edge, and then also one is smack dab in the middle, and then they filled up the rest of the box just like that. And so we put a lid on it. There's a lid back there. We put the lid on it and we monitor that. And the purpose of this is to determine the maximum heat rise. That's that adiabatic heat rise. Now this is definitely not adiabatic testing the way it would be done in a laboratory. It just gives us sort of a feel for the concrete that's being generated, the mix design. Because adiabatic testing is a very specific process. And at that point, once we know that the mix design is capable of not blowing past our peak temperature, then we can use it in the field. And these are just some pictures of a large mass concrete job that we're currently on. We have lots of sensors that are going down inside a very large drilled shaft. The sensors are all strapped up to this giant cage that is then lifted and placed, put inside the hole, and it is a huge project. I think these were 100 and something feet deep. We needed to monitor from about the midpoint on up, and so we had sensors that were placed all throughout this cage, and then the sensors actually came up and over this collar here. And if you can see where my mouse is, we've got our devices sitting there recording all of this. And so when you record all of this temperature, and it may be a little difficult to see, but this is some of the summary data that we were able to collect from that particular test pour that we did, where we had the temperature at a depth of 50 feet, 50 feet of concrete. The centroid, the peak temperature was 142 degrees, well within the maximum temperature that they could experience. So they were well within that. The mix design was working beautifully. The edge, which is right along the side where the earth is, was only 115 degrees. So the delta, the maximum delta between the centroid and the edge was about 29 degrees, a little bit below that Fahrenheit, which means that again, the mix design is doing exactly what it's supposed to do. You're not going to have too much thermal stresses. We also were able to, because of maturity, we were able to evaluate the strength of this concrete as it's curing, and it took a certain number of hours to reach, for example, 3,500 psi, and then 5,000 psi. And those are important numbers because what we don't want to have happen is you don't want to have one area of the concrete that is much higher in strength than another area of the concrete, because that can also cause some stresses. And it was pretty interesting that the temperatures, we had a peak of 142 degrees, but then by day 5 it had dropped down to 124. So and then by day 10 it had only dropped another 4 degrees. So this concrete was hydrating slowly, and it was doing exactly what it was supposed to be doing. This is a graph from our software that shows actually the in-place temperatures. The red line represents the center graph, the center temperature history. The blue line represents the edge temperature history, and the green line down here represents the delta between them. So you can see that we had a peak delta of just under 30 degrees, and then that nice smooth uh, lowering of the delta over time. This is almost an ideal mass concrete uh, temperature graph. Just a couple other pictures of some other drilled shafts that we've done. Some of these are pretty amazing. This one was huge. It was in Chicago, and you can see some of our devices. We've got the sensors lined up along there, and this thing was huge. And you can see, the guys are lowering this down inside the hole there. So using temperature probes, what we can do is we can monitor the central core and also the outside edge or the face temperatures, and it gives a clear indication of the status of the concrete at any given moment in time. One of the other things that you can do is you can use maturity to determine the in-place strength of the mass, which in some cases can allow the differentials, the maximum differentials, to be allowed to be increased gradually because the concrete can withstand the tensile forces that are acting upon it. And really, what that basically means is that you have the opportunity when you use maturity to use the maturity system to determine the maximum temperature allowance based on the strength of the concrete. Initially, that you may have a limitation of no more than 35 degrees difference between the core and the outside edge of that concrete. But as time goes on and that concrete gains more strength, the concrete can withstand higher differentials. So, for example, once that concrete reaches, let's say, 2500 psi, you can go from a maximum of 35 up to 40 degrees. When the concrete reaches 3000 psi, you might be able to go from maximum differential from 40 up to 45 degrees. This can have a huge impact on construction, on the pace of construction, how quickly you can strip forms, remove blanketing, things like that. I will say, though, that thermal modeling is required to determine the rate of this increase in allowable differential temperature. So it's something that is definitely you should talk to an engineer about that, but we've definitely done this on several projects. Here's another example, a couple other pictures of some mass concrete and customers placing sensors down inside the mass, and they'll place sensors at strategic locations in the core and the outer surface, and then of course they'll uh, make sure that the concrete gets protected, because what you want to do is when they place the concrete, they don't want any of that heat escaping. I know this was a very cold day when they placed that concrete, so they wanted to make sure that they had heaters. They actually ran heaters inside to keep all the concrete warm, which is counterintuitive when you're talking about trying to keep the heat down. But the mix design was right, and they had plenty of heaters to keep everything warm. Here's another example of pretty common example of mass concrete today. This happens to be a wind farm pedestal, so a wind turbine tower pedestal. So you have many examples of massive concrete that's out there today. This is heavily reinforced. Obviously, we've got sensors that are running down inside the core, and they run out into certain areas of the concrete. So as far as mass concrete goes, as I said, this is mass concrete light because there is so much to talk about. But what you should know and what you can plan for is you should understand the concrete fresh performance, how it's going to perform thermally, what your peaks are, what your delta is, what your maximum temperature rise is going to be. You need to understand if that mix is going to be workable and pumpable for you. You need to understand the water requirements because typically for mass concrete, you're going to be working with some relatively low water cement concretes that may be very difficult to work with. And it also, you should be aware of your admixture requiremements, knowing that knowing all of this, you can actually use admixtures to your great advantage. The early age properties are really that's what you really want to focus on with sensors, and that's where having sensors in place, monitor that live data, and monitor the some test cylinders too. That's great for comparisons, but definitely monitor the live data because you have to monitor typically for mass concrete you have to monitor um, the concrete core and the outside edge, and typically you'll also have to do redundant core and outside edge sensors. And I will say that it would be great to be able to put the maturity method, the ASTM C1074, to work, and it should save you time, and it'll take a lot of the guesswork out of mass concrete. If you use thermal modeling and you look at how that maturity can allow your maximum differentials to be increased over time, that can save tons of time because it can allow early cessation of protection and insulation, and it can even allow early form stripping. And to finish up, definitely want to make sure that uh, everyone has the latest copies of 207.1 and 207.2. Those two guides are fascinating to read. They will give you a ton of great information about how to properly do mass concreting in the age uh, of wide variety of cementitious materials. And remember, durability is always the goal. That's what we always strive for, and that means no thermal stress cracking. So if you can do that, then you are winning the mass concrete battle. That is for sure. So thank you again for your time. I really appreciate it. I hope this was helpful. I know it was sort of disjointed a little bit, and I apologize for that, but it's a very wide ranging subject, and it was a little difficult to get my arms around it for the purposes of a 25-minute webinar. There's a lot of good stuff out there, and we can certainly help out with the monitoring aspects of it. Thank you very much. There's my contact information. Contact me via email, or that's my direct cell phone number. And if you happen to like this webinar, you can also catch us next week if you guys are in the precast business. Holy cow, I do know what I'm talking about in precast. It should be really interesting because maturity is going to transform the precast market greatly. So that's what we're going to talk about next week. So thanks again for your watching, and have a great day.